Hello, this is a video for you if you're interested in getting a big review of all of the topics that we've covered so far, the topics that are on your test. We've done so much good work condensing and expanding logs, evaluating logs, setting them in real life examples. Old essential questions that we've covered are: how can we use product quotient power law to condense and expand logs, and what are we looking for when we evaluate a log? I'll go over these two questions briefly here. If you're not familiar with them, stay with me and we'll go over them now. If you'd like to skip, you're welcome to skip. So these are the log laws: product quotient and power law. We can see they're expanded and they're condensed versions. We can use these laws to manipulate the way that the expression looks so that we can more easily solve for our unknown value. For product law, we see it expanded with our addition sign, and to condense it, we're going to multiply these two terms with the same base 3. For quotient law, instead of multiplication happening in the condensed form, we see division. There's a fraction. We also know quotient law is at play when we see a subtraction sign. For power law, my personal favorite law, because it is so powerful, we can take this exponent 2 and we can bring it down out in front of our log as a coefficient. The second essential question that we're reviewing is: what are we looking for when we evaluate a log? What we are looking for is the exponent. When we evaluate this log, 1/2 of 8, we're looking for x. What is the exponent that I need to raise my base of 1/2 to in order to get 8? How many times do I need to multiply 1/2 by itself to get 8? This is where power tables can be really helpful. Another example of a logarithm: log base 3 of 27 equals x. When we evaluate it, we're looking for what is the number that I need to raise 3 to get 27. Power tables are one way that you can handle this logarithm and look for this value, this number. We know that we can raise 3 to the 3rd power to get 27. The trick that we used here in the second step is we changed 27 to base 3. Once we found our common base, we were able to cross that base out and just set the exponents equal to each other. Moving on, so the questions that we're going to focus on for the rest of this review video are: how can we use logs and the laws of logs to solve for values in real life? And we'll see an example with money. Also, I want you to think about: can you divide by entire logs to get the variable alone? So can you use inverse operations even with a whole log to try to get x alone? Here's our example. We're looking for time. How much time will it take to accrue double my money if I invest $600 at an interest rate of 12% compounded monthly? It may seem a little hairy. There's a lot of facts in this problem, but when we remember our equation, this formula for exponential growth of money, we can start identifying what all these numbers are. We know that A is going to be the total value, the number that we're going to get at the end, and the principal is going to be what we're starting with. So our P can be 600. We're starting with $600, and we're going to try to double that. So 600 times 2 is 1,200. And at the end of all this exponential growth, we want to get $1,200. And we're solving for how much time that's going to take. All right, other values that we can plug in are interest rate. They gave us is 12%. So that'll be 0.12 or 12 at 100. And if it's compounded monthly, then we can use this number 12. there's 12 months in a year. So to start solving for t, we can start by using inverse operations. Let's get rid of the 600 right away. On the right, it crosses out. On the left, 1200 divided by 600 is 2. We can also start simplifying this inside of the parentheses. If you take out your calculator and plug in 0.12 divided by 12, you'll get 0.01. Add that to 1, and we've got 1.01. Before logs, this is where a lot of people get stuck, because how can you solve for an unknown value when it's in the exponent? You know how to use inverse operations when this exponent is down on the ground. But when it's all the way up here, it's a little bit harder to find. What number do you need to put here? What do we need to raise 1.01 to times 12 to get to? It's a little hairy and it's hard to find. So this is where logs are really valuable. Let's take the log of both sides so that we can use log laws. We can use the power law to take this unknown exponent and put it out in front. Then remember your essential question. Can you divide by a whole log? You can. To try to get this log alone, you can divide by log base 10, 1.01 on both sides. On the right, it crosses out. And on the left, we need to simplify it. Using a calculator, log base 10 of 2 is 0.301, and we'll divide that by, that was 0.301, dividing by, we need log base 10, 1.01. This Chrome extension is a little annoying to use, so I apologize for the technical difficulty. All right, so this was the value of log base 10 of 2, and we're dividing it by 1.01. I'm taking the log of that. There we go. We should get 69.661, and then your last step is just to divide by 12 on both sides. To get the t alone, it'll take 5.8 years. How did we know? We used logarithms so that we could use the power law, get the exponent down on the ground so that we could solve for it. We also learned that you can divide by an entire log to isolate a variable. All right, that's it for this review video. Please reach out if you have any questions, especially if you have questions about which calculator to use. You definitely need one with log. And this Chrome extension I don't totally recommend, but there is a really good one on your phone that you can download if you don't already have it. So let me know if you do need a calculator, because you will need to do these calculations with logarithms. All right, have a good one. Hope this helped.